In this lesson, we're just going to walk through how to rationalize the denominator of a fraction and also talk about rational exponents. So for example 1, we want to rationalize the denominator of 3 over the square root of 12. We say that this has a monomial in the denominator because we only have one term. So when we have a monomial in the denominator, our first step is that we want to try to simplify the radical if possible. So the square root of 12 I can simplify because the largest perfect square factor would be 4. So I can rewrite this as the square root of 4, square root of 3. And then the square root of 4 becomes 2. So simplified, I can rewrite this original fraction as 3 over square root of 12 simplifies to 2 square root of 3. So first we want to try to see if we can simplify that radical. If we can, simplify it. If not, then we need to look at the type of radical that we have. So most of the time you're going to be dealing with square roots. That's what I'm going to address here, is that when we have a square root in the denominator, in order to rationalize, we can multiply the numerator and the denominator by the exact radical that we see. Because the whole idea of rationalizing the denominator is to get our radical out of the denominator. So if I multiply the numerator and denominator by just the radical that we have, this square root here. So I'm just looking at that square root of 3. So square root of 3 to the numerator, square root of 3 to the denominator. Then what we have is in the numerator just 3 square root of 3. And then in the denominator, working this out, I would have, there's really a 1 in front here if you want to think of it that way, because you're multiplying your numbers in front, so 2 times 1 is 2. If we multiply the numbers underneath, square root of 3 times square root of 3, 3 times 3 would be 9. So we would have the square root of 9. Well, remember that the square root of 9 is just 3. So we actually have that this is equal to 3 square root of 3 over 2 times 3. So with rationalizing, we can see that when we multiply by that radical, that same exact square root of 3 times square root of 3 becomes square root of 9, but then the square root of 9 is just 3. As shorthand, you can just skip that second step and say square root of 3 times square root of 3 comes out as just 3. So with square roots, that's why we can multiply the numerator and denominator by just a square root. Continuing to simplify this then, we have that our denominator would be 3 times 2, which would be 6. And then next we want to reduce. So our last step is just to simplify our fraction that we have. So finally we would end up with 3 and 6 would just reduce to 1 and 2. So the 2 would be in the denominator. So our final answer would just end up being square root of 3 all over 2. So that's rationalizing the denominator if we have a monomial square root in the denominator. So in this example, we want to rationalize the denominator of a fraction that has a binomial in the denominator. So we have two terms. We have 3 square root of 2. We have a 4 separated by a plus, which means that we have a binomial. So when we have a binomial in the denominator, and again, we have a square root, the way that we want to rationalize the denominator is by multiplying the numerator and the denominator by the conjugate of the denominator. Now, the conjugate, remember, of a binomial will be the same terms but different sign. So if I had 3 square root of 2 plus 4, which I have right now, the conjugate of that would be 3 square root of 2 minus 4. So that's what we're going to do. We're going to multiply the numerator and the denominator by 3 square root of 2 minus 4 and 3 square root of 2 minus 4. So that shows the conjugate of the denominator. For our numerator, in order to simplify this, we would just multiply and distribute. So I'd be doing 8 times 3 square root of 2, which would give me 24 square root of 2. Then I'd be doing 8 times 4, which would be 32. So I have minus 32 in the numerator. Now the denominator, I'm going to move this over and work this out to the side, so that we can see what happens when we're multiplying. So we're doing here 3 square root of 2 plus 4 times 3 square root of 2 minus 4. If I'm working this out fully, I need to distribute or FOIL. So if I'm multiplying 3 square root of 2 times 3 square root of 2, that would be 9 square root of 4. Distributing the 3 square root of 2 to the 4, we would get minus 12 square root of 2. Multiplying on our inside, the 4 distributing, we'd get 4 times 3 square root of 2, which would be just what we had previously, but a positive or a plus 12 square root of 2. And then last, we would have 4 times negative 4, which would give us a minus 16. At this point, then, we would want to simplify and combine like terms. So by simplifying, I mean I have this square root here of 4. So the 9 would say the square root of 4 is 2. Next, I can combine like terms. If I look at my two middle terms, the minus 12 square root of 2 plus 12 square root of 2, those are like radicals, so I can combine them. But negative 12 plus 12 is 0, so these actually cancel out, which is a good thing. Anytime that we multiply conjugates, those middle terms should cancel out. That's a way to check to see if you're doing your math correct. And then we still have that minus 16 at the end. So here, 9 times 2 would be 18. Minus 16, we'd be left with a 2 in the denominator. So a few comments here is that when we're multiplying conjugates, your middle terms should cancel out. So I really could have, from the beginning, back up top, done 3 square root of 2 times 3 square root of 2, multiplied your first terms, and then multiplied just my last terms. And if I did that, then I would have skipped having those middle terms that we knew were going to cancel out. So it is okay to just multiply your first and your last terms as long as they are conjugates of each other. Also, remember, square root of 2 times square root of 2 is square root of 4, but that simplifies to 2. So if you'd rather not write square root of 4 and just say square root of 2 times square root of 2 is 2, that's okay as well. Finally, we do want to simplify this. So one method of simplifying would be to take the 2 and divide it into each term in your numerator. So that way we would have 24 over 2 is just 12. Square root of 2 stays, minus 32 divided by 2 would be 16. So when we rationalize the denominator, we get a final answer of 12 square root of 2 minus 16. Next, we get into our rational exponents. So if the nth root of a represents a real number where n is greater than or equal to 2 is an integer, then we can say that a to the 1 over n is equal to the nth root of a. So what this really means is that we can rewrite a radical with a fractional exponent or a rational exponent. Further, if we have a to the negative 1 over n, that negative exponent rule again would flip it over, take the reciprocal, so it would be 1 over a to the 1 over n, which would then equal 1 over the nth root of a as long as a doesn't equal 0, because that would make the denominator undefined. So for example, if I had 4 to the 1/2, using this rule then, I can rewrite this as with a root. The 4 would be underneath, right? That's the a that we're talking about. And then 1 over n is your root. So I would have a 2 out here. Well, the 2 means that we're taking the square root. So I can really look at this as the square root of 4, and we know the square root of 4, again, as we just saw, is 2. Similarly, if I had 8 to the negative 1/3, that negative exponent means we have 1 over 8 to the positive 1/3, which I can then rewrite as 1 over, we have a root, we have our 8, and then the 3 tells us what root we're taking, and we're taking the cube root, so we put the 3 on the outside. The cube root of 8 then would just be 2, since 2 to the 3rd gives us 8. So our final answer here would be 1/2. So really just understanding that notation and how to write with the fractional exponent and the radical. This concept is going to continue to come back. Even more with our rational exponents, if the nth root of a represents a real number and m over n is a positive rational number where n is greater than or equal to 2, then a to the m over n equals the nth root of a raised to the m. So we're adding this extra piece where we have not a 1 in the numerator, but we have a number. Same thing is that we can rewrite this second part as the nth root of a all raised to the m, is that we can bring the power inside and it's okay, so the nth root of a to the m inside. Really how you want to think of this is that you're going to have a to your power or your exponent over your root. Okay, so there's lots of letters involved, but between the last slide and this slide, whenever you have a fractional exponent, you're going to have whatever the number is to the power over the root. So same thing with your negative exponent. If I have a to the negative m over n, you're going to have 1 over a to the m over n, which again would just be 1 over the nth root of a to the m. So again, really lots of letters, but you want to think of it as a to the power over root, or whatever your value is. So let's just see how these rational exponents work in terms of simplifying. So if I have 27 to the 4 thirds, we again want to think of this as our power over our root in terms of how we want to set this up. So we know that I have some sort of radical. Okay, I don't know what kind of radical, but I know that I have some sort of radical. The 27 is going to be inside. Our power is 4 because that is our numerator, so power over root, and then our root would be 3. So again, there's a few ways how you can write this, that you can have your power on the inside like this to the 4th, and then our root has to be on the outside written like this. Or typically with numbers, it's easier for you to use that second method or the alternate method where we have the power on the outside. This way, when we're taking the root of a whole number, you're going to get a smaller whole number, so it'll be easier to raise to the power. But either way will work. You can use your calculator and figure out what 27 to the 4th power is. But typically, like I said, with numbers, we leave the power on the outside. But either way, from here, we just want to evaluate this. So working inside our parentheses, the cube root of 27 would just be 3. Still raised to the 4th power, and then 3 to the 4th is going to be 81. So 27 to the 4 thirds power is really equal to 81. Same idea with our 32 to the negative 2/5. With that negative 2/5, we do want to rewrite this first as 1 over 32 to the positive 2/5. Which then means, again, we have 1 over some sort of root. The 32 would be inside. Again, that 2/5 means that you're going to have your power over your root. So our root is 5, our denominator, and we're going to be raising it to the 5th power. We're going to be raising it to the 2nd power. So we have 1 over the 5th root of 32 raised to the 2nd power. So we do need to figure out what the 5th root of 32 is. So what number to the 5th power gives us 32? It is 2. You can verify that with your calculator. So we're left with 1 over the inside became 2. So we're left with 2 squared, and then just evaluating 2 squared, we're left with 1/4. So 32 to the negative 2/5 is really equal to 1/4. You can do this in your calculator to check. What you would do is, if you're doing either one, 27 to the 4 thirds, you would type in 27, use that caret, and then you need to use parentheses to do 4 divided by 3. If you don't use parentheses, it's going to raise it to the third, excuse me, it's going to do 27 to the 4th power, get that answer, and then divide it by 3. Remember, your calculator does order of operations. Without parentheses, it's not going to do that first. Same thing, you can check the 32 to the negative 2/5 in the same way.